welcome back everyone. Thank you for coming back. So next up we've got Daolang Huang from Aalto University.
All right. So I think everyone's here, so I will just start. So hi everyone, I'm Daolang Huang. I'm currently a third-year PhD student at Aalto University in beautiful Finland. So I'm co-supervised by Professor Samuel Kaski and Professor Luigi Cherby. So before this talk, I would like to first thank the organizers to have me here. So as a junior researcher, it's really a great opportunity to speak here and share my work. So my PhD goal is about building different amortized methods in order to accelerate both the Bayesian inference, for example, like simulation-based inference, and the data acquisition, for example, like Bayesian experiment design and active learning. So for today's talk, I will first briefly introduce what is amortization, although I think most of you have more or less some understanding about it. And then I will introduce a family of the amortized or meta-learning methods called conditional neural processes. Things like Desi already gives some high-level introduction about the Bayesian experiment design. So in today's talk, I will try to go deep into the network part to teach how to build your own policy based on the current state-of-the-art model. So, and then I will introduce a very flexible inference architecture called amortized conditioning engine. And in the end of the talk, I will introduce my latest work called amortized active learning and inference engine, which is capable of doing both Bayesian inference and data acquisition. So I think this work is actually quite related with this, the theme of this workshop. So I'm really glad that I could finish the paper just right before this workshop. So I will just start. So in many critical fields that we face two fundamental challenges. The first one is about data acquisition. So it's about how do we select the most informative data to collect, or how do we design experiments under the limited resources or some constraint. And then the second challenge is about statistical inference. So how do we reliably reason and make predictions based on our collected data that are coming from the data acquisition process? So a lot of problems can be formulated into this loop. For example, we have some belief about this word, and we're trying to optimize our next design, and then we do some experimentation and get the outcomes of it, and then we update our belief, and we do it again and again. So a lot of problems like personalized medicine, or material discovery, or human-computer interaction. So a lot of problems that trying to interact with human will fall into this loop. So regarding the data acquisition, Desi yesterday already introduced a very powerful framework called Bayesian experiment design. So the idea is we try to guide and optimize the experiment design X aimed at reducing uncertainty about parameters theta of the system or of the world. So how do you do that? We usually just maximize the expected information gain of the parameters, although we could have some downstream utility. But usually in this community, people will care about expected information gain. So the problems of the calculating the expected information gain is it's very expensive and usually intractable. So in order to get the next design, we usually need to spend a lot of computation on that, but that's not the ideal case. Okay. And then for the statistical inference, of course, we have the Bayesian inference framework. And as Jeremy has introduced yesterday, so the core idea is about update our belief about unknown parameters data after observing the data. So how do we do that? We just apply the Bayes rule to compute the posterior distribution given some prior knowledge and data. Okay, and the problem is those gold standard methods, for example, like MCMC, they are very powerful, but they can be very slow. So, okay, but in many different applications that we are in the race against the time, where every second is critical, so we need to rapidly decide which data to acquire next to maximize our knowledge. And also we need to rapidly learn about these non-known factors based on the collected data. So for example, in the disaster search and rescue, that we need to rapidly decide the next area for drone exploration to maximize the chances of finding survivors. And we also need to rapidly estimate the survivor locations from those incoming sensor data to guide the rescue efforts. So it's about acquisition first and then do the inference. And both things need to be super fast. And also, for example, in the emergency patient diagnosis, that we need to rapidly determine an optimal sequence of diagnostic tests to quickly identify the patient's condition. And we also need to rapidly infer the patient's illness based on the unfolding test results to enable the timely treatment. Okay. So how do we do that? How do we speed up the Bayesian inference and data acquisition? So the solution is just through the amortization. So to my understanding, amortization means that we are trying to shift the expensive computation offline by pre-training the neural network on a vast numbers of simulations or pre-collected data. And our idea is to try to meta-learn how to map a problem feature directly to its solutions. And once we build such a powerful neural network, at deployment stage, we can just provide the solution instantly in just a single forward pass. So right figure shows the illustration about amortization. So without amortization, in the deployment stage, whenever we have some new data comes in, we have to spend same amount of the efforts to get our quantities of interest, and we have to repeat this process again and again. But with amortization, how about we just shift off the computational cost into the training stage and build such a very powerful neural network, and when in the deployment stage, whenever there's a new data comes in, we can just throw in the neural network and get the answer. So that's it. Okay, so as I mentioned before, the problem in the traditional BED is the slow computation for each designs. So we have the amortized BED or policy-based BED methods. The core idea is we are trying to learn a policy network pi offline. And how do we do that? We just pre-training on simulated experiment design trajectories to directly map a data history to the next design. And then once we have this kind of policy, then propose the next design becomes an instant forward pass. And the problems in the traditional Bayesian inference field is applying those methods MCMC can be expensive. So actually it's then we have the amortized inference method. So it's actually a very large field containing a lot of small directions. So today I will only cover 2 small directions. The first one is if we are trying to amortize in the posterior, then care about some underlying status of the word or of the simulators, then we have the neural posterior estimation or NPE method. The core idea is to directly learn a neural density estimator Q5. So this Q5 could be any density estimator like normalizing flow or flow matching models to directly approximate the true posterior. And how do you do that? We just pre-training the network on a lot of simulated pairs. So here we assume that we have a simulator which can represent the true generating process of the word. So the input of the simulator is just a parameter that draw from some prior distributions, and output of the simulator is just the simulations. So using this simulator, we can gather a lot of simulated pairs, and then we can train over this kind of the simulations. So idea is then we can pass into the neural network. If we care about posteriors, then the input is the data, and output is the approximated posterior of the status. And once it is trained, we can just throw in some new observed data during deployment stage, and we can immediately get the posterior that we want. And in this field, currently I assume that in this work, I assume the simulator is well specified to the real-world generating data. But of course, there are a lot of important work that are dealing with the model mystification, but that's not our focus today. Okay, and for amortized posterior predictive, then we have the conditional neural processes. I'm not sure how many people have heard conditional neural processes before. So, okay, so not so many people. So the conditional neural process is the major goal is we are trying to predict future data, py star given the x star and data. So data is our observed data, and x star is the corresponding future, x star is the future prediction, the input of the future predictions. And we are trying to effectively learn a distribution over functions. So you can think it as a counterpart, neural network counterpart to a Gaussian process. But the idea is we are trying to meta-learn over a lot of different functions. So I will go deep into the conditional neural processes. So the same piece actually instantiates so-called prediction maps within a neural network. So what is exactly a prediction map? So prediction map pi takes the following format. So it takes in, it has the dn, which consists of x and y pairs, and we call it the context. So that's our current observed data so far. And x star and y star are our targets. So given some x star, we are trying to predict y star. So it's like a regression problem. And h is just the learned neural networks, which takes in the x star and dn and trying to predict the distribution about the y star. And in same piece, each of the py star given the h, x star, and dn is modeled as an independent Gaussian. So the idea is we just taking the data into network and output mean and standard deviation about the y star. So that's very simple. Okay, so to train a conditional neural processes, we first, for each round, we first randomly pick generate the data set. And we have some data points, and we divide those data points into the context set and target set. So maybe this red is not very clear here. So so here we have x1, y1, x3, y3, and x5, y5. We assume that we observed these points already. And we treat those x2 and x4 and x6 as the target set. And the idea is we are trying to predict the targets given the context. And how do we do that? We just do the maximum likelihood training. Okay, so during training, because since it's a meta-learning model or amortized model, so that we are trying to learn over a diverse collection of functions. So here are some functions that randomly draw from GP. So it's just to show that during the training, we are learning over a lot of different functions in order to cover like this such space. And then at test time, we can make instant predictions for targets given any new context set on our new functions. So basically, essentially, we are doing the in-context learning. Okay, so there are like a lot of different neural processes has been proposed so far. So for example, the original CMP and also the corresponding, there is attentive neural processes which use the attention mechanism, and also convolutional neural processes and equivariant neural processes which trying to build exact translational equivariance or other equivariance into the neural network. So that's about like inserting the inductive bias into the neural network. And then and then we have the transformer neural processes, which can be regarded as the like current general purpose state-of-the-art method. That's also the thing that I would like to introduce today because of the like my work is built upon these transformer neural processes. And recently there are also some large language model based processes which directly use the large language model to predict data, but that's not what we are going to cover today. Okay, so now I will introduce the transformer neural processes. So actually it's quite simple and standard. So remember that we have context set and target set before. So we have some observed data as the context set, and we're trying to predict the target set given some X star. So then we first map them into the embedding layers. So X has its own embedding layers and Y has its own embedding layers, and then we map them together and to this embedding space, high-dimensional embedding space. For example, for context set, we just combine the X and Y's embedding, and for target set, it's just the X embedding. So once we get this kind of embeddings, then we can pass into the transformer layers. So for the context set, we just use the multi-head self-attention. So this MHSA allows every context point to look at each other, and we are trying to exchange informations with with each of the other context set. So we are essentially trying to learn those underlying patterns from or underlying structures of the function from the context set. And once we have the representations of the context set, and then we can use the cross attention between the target set and the context set. So the idea is each of the target points is attend to the each of the context set. So the idea is we allow each target point acts as a query to our context set. Then attention mechanism just compute how relevant each of the context point is to the target points. Okay. And once we get the refined representations of the target set, we just input of them into the inference set. So the inference set is just a very simple MLP, and it outputs, for example, in CMP, it outputs the Gaussian distribution, so it outputs the mean and standard deviation about the Y star, and then we compare with the true Y, and then we use the maximum likelihood to update our neural network. So that's very simple. So the CMP, especially the TMP, they are very excellent at modeling this PY star given X star and the DN. But problems is like all existing neural processes can only work with the data. But as I mentioned before, like many problems are like in Bayesian inference that we care about some task relevant latent parameters data. So we often want to predict this latent. So it's about infer parameters from the data. And we also want to conditional on our knowledge about this latents to improve other predictions. So for example, you have some prior knowledge about data and you're trying to condition on this prior knowledge and make a better prediction about future data. So how can we do that with the neural processes? So there are actually a lot of problems that we are conditioning on part of data and latents, and we are predicting the rest of the data and latents. For example, for this like image completion and classification that we have part of the pixels as the data, and we are trying to complete the whole images. And for the latents, we have the labels of the images as the latent. If we assign like a very non-informative prior to the latents, then the network is very uncertain about its prediction, and also it will give very uncertain prediction about its label. But if we assign some very strong prior knowledge, okay, that's 3, then the network will become super confident and it will produce a 3. And of course, the latent is also 3. And then for Bayesian optimization, the task is to trying to optimize the black box function given some observations. And so we care about the location of the optimums or value of the optimums. So here we can treat the location of the optimum xopt and y optimum, that the value of the optimum, as the latent informations. And then the network is trying to like build a surrogate model based on the observed points, so we have some uncertainty estimation, and also because our essential target is to estimate the distribution of the x optimum and y optimums, that we also trying to let the neural network directly estimate them. And the last example is about simulation-based inference that I mentioned before in the neural posterior estimation part. So the idea is that we are given some observed data and also maybe some prior knowledge about theta. And the idea is trying to predict the rest of the data if there are some missing data during the observation stage. And also we are trying to update our beliefs about theta given the observed data. So you can see a lot of problems actually fall into this region. So, okay. And so we are interested in modeling not only about data, but also task-relevant latent variables. So how do you do that? It's very simple. We just we propose this called like amortized conditional engine. So this engine doesn't mean anything. It's just that we need that E, so we get ACE. So the idea is we're trying to like straightforwardly like extend TMP to include this explicitly defined latency information theta. So now with this, before the neural process can only work with data, but now we can actually conditional theta and predict the theta if we have some theta information, or we care about the posterior of some latent information. Okay, so the architecture itself is like also very simple. That's the original transformer neural processes. Okay, so in order to incorporate different latent informations, we have this L and theta information. So L here is just the indicator of the theta. So for example, we have like 3 different thetas, then we can just assign different indicators for each of theta to indicate this is the theta that we interested. So if we have we know the theta 1, then we can actually combine with the L1 and input into the transformer layers. And also if we care about predicting the theta 2, then we just insert the L2 into that. So super simple. And another thing that are different to the original CMP is that we replaced the original Gaussian distribution with the Gaussian mixture model in order to model more complex distribution about theta or data if the theta is like multimodal. So, and then the training is the same. We just use the maximum likelihood training. And then with this framework, we can actually do a lot of things. Like for example, for the conditional image generations completion, that we have part of the images or part of the pixels, and we're trying to like complete the rest of them. So now the latents we can assign some latent information. For example, if we assign the body equals true, it will generate some bald man and bald woman. If we assign the body equals to false, then we can actually generate some hairs. And then for the Bayesian optimization, the original, like for example, other neural network methods can only model the surrogate model, like build surrogate model based on the some observation, this black point. So with ACE, we can also build a surrogate model. So we can replace the Gaussian process, and we can also see like it offers relatively like good uncertainty estimation, but of course not as good as the Gaussian process. But another thing is that we can directly model the PX optimum and given the DN, and PY optimum given the DN. So because that's the thing that we are essentially care about. And with this explicit estimated distribution, we can use them to optimize our acquisition functions. For example, like Thompson sampling, then the draw samples from it will become super easy. And of course, like in maximum entropy search, this distribution are like intractable. So, but now we have this kind of direct estimation, so we can just replace this intractable distribution with our tractable distributions. Okay, so except for those things, ACE can also offer the prior amortization. So which means that we are trying to specify some prior knowledge at the inference time without retraining. So what does it mean? So it means that we often have some prior knowledge about theta, and we are trying to incorporate this prior knowledge into the neural network. But previously, all of the amortized method, if you change the prior, you have to retrain the whole model again. But now ACE offers like prior specification in the training stage, in the inference stage. So how do you do that? So it's also quite straightforward that we just discretize the p theta as a histogram. So that's just a vector of the probability over a predefined grid. So if we have like 100 bins, then we can just represent these prior distributions as 100 numbers. And then we can just incorporate it into the neural network. So how do we do that? It's also straightforward. We can just combine the prior knowledge with the, for example, the indicator of the theta. So if we are trying to predict the theta2, then we can, like, if we have some knowledge about theta2, we can just input it in the context set, and then we can do better prediction, or like based on the different prior knowledge. Okay. So I will show you an example about prior amortization. So here is the toy example that we are trying to infer the posterior of 1D Gaussian parameters. So that's the mean and the standard deviation of the Gaussian distributions. And we have the data that are drawn from these Gaussian distributions. So that's the likelihood. And we can just randomly assign some different prior knowledge about mu and sigma. So that's mean and standard deviations. And then we can actually get the true Bayes posterior because everything is Gaussian. So that's the true Bayesian posterior based on the prior and likelihood. And then we also compare with the ACE posterior with the true Bayes posterior. We can see actually ACE can estimate the true posterior quite well. But for ACE, we don't need any retraining during the deployment stage. We can just insert different prior knowledge and get a posterior. That's it. Okay, so ACE actually provides a solution for a very flexible amortized inference. But can ACE do everything? No, so don't forget that we have a second challenge. So that's about the active data acquisitions or experiment design or active learning. So the ACE actually totally relies on the passive data collection. So it can only do inference based on the data that we provide to him. But it doesn't have any capability to actively curate the data points. So unfortunately, the progress in these two different fields, like the amortized Bayesian inference fields and amortized BD fields, are largely developed in parallel. So the amortized Bayesian methods, like inference methods, they can't intelligently collect the data. So they have to rely on the passive data collection. And for the amortized BED, as Saho and Desi introduced yesterday, so they can provide very informative data points, but they can't perform inference efficiently once we have collected this data. But in a lot of cases, we care about the posterior or posterior predictive about these informations of the things that we're interested in. Okay, so in the most general and challenging task that we need to rapidly select the most informative data to query, and we also need to rapidly perform inference based on the collected data. And as I mentioned in the beginning, there are for example, in the rescue efforts, like a search example. And there is actually another requirement for it. For example, like the data acquisition, the collection strategy often shift if the goal changes. So in order to do that, we need to flexibly adjust our query strategy based on different goals. And also depending on our different goals, we may only interested in a subset of the parameters. So there might be some nuisance parameters that we don't care. Or we sometimes care about this subset of parameters, and sometimes we care another subset of the parameters. So I will give you concrete examples here. So this is the psychometric functions that very commonly used in the psychometric experiments. That's the idea of the psychometric experiments. That is, we are trying to infer an individual's behavior parameters from its responses to varying stimuli. So here, this psychometric function is controlled by 4 different parameters, so you don't need to know exact meaning of this function or the meaning of the parameters. So you just need to know there are 4 parameters, and if we focus on the perceptual sensitivity, for example, then we only need to care about threshold and slope, but we don't care about guess rate and lapse rate. Those are the nuisance parameters that we don't care. But if we focus on the response bias or the attentional phenomena, for example, when we are dealing with the animals, then we care more about guess rate and lapse rate, but we don't care about slope and threshold. Okay, so how do we for example, flexibly adjust our query strategy based on different goals and using just one single network? So that's the idea about the amortized active learning and inference engine, and we call it a line. So with the line, we can instantly estimate posterior or posterior predictive distributions, and we can also instantly propose the next informative design to query, and also we can offer the flexible adaptation to its own to its inference and acquisition strategy to different specified goals. So we compare our method with our previous methods. For example, for the neural processes that I introduced before, it can only do amortized inference for the posterior predictive, and for the neural posterior estimations, it can only amortize the posterior. And for DAD and RBOED or ILCC, this kind of the amortized BED method, they can only amortize propose the informative design for some underlying parameters. And also there's a recent work called amortized active learning, which can propose the designs for some future predictions. And of course, this Jana, Informer, and ACE that I introduced before can do flexible inference, but they cannot collect the data actively. But with the Align, we are the first work which can do both things. Okay, so now I will introduce the Align. So to recap, that we have the input X, so that's about experiment design or covariance, or the thing that we care about. Then the output is just the Y, it's a corresponding outcome, experimental outcomes. And we assume this model is parameterized by some like underlying vectors theta. And we also we can call our data collection as the X and Y pairs, so dt. And we also have the likelihood. It could be checkable or incheckable. So if we care about the posterior, so that's about theta space. So it's just corresponding to the likelihood and the prior distribution. But if we care about posterior predictive, so that's about some future prediction points like the X star and the Y star. So then we care about this the py star given the X star and marginalize the posterior. And in order to quantify the information of the data points, then we have the expected information gain. So that's the EIG just over the one single experiment. So that's about the expected entropy difference between the prior and the posterior. And if we care about posterior predictive, then we can use the corresponding expected predictive information gain to quantify. So that's just the difference between the EIG is that we are quantifying over we are evaluating the entropy over the predicted distributions, py star given the X star. Okay. So for the problem setup, as I mentioned before, the Align need to flexibly to deal with different targets. So how do we do that? We first introduce a so-called target specifier CASI. So this CASI is to indicate our interest. So for example, we have the parameter targets. We call it CASI theta s. So the goal is to infer a specific subset of the model parameters theta s. So S here is just the indicator or index of the different thetas. For example, S equals to 1 and 2 means that we care about the theta 1 and theta 2. For example, S equals to 1 to L, it means that we target all parameters, so it's aligned with the standard BED literature. Okay? And we also have the predictive targets that we call it the CASI Y star given the P star. So the goal is to improve the predicted distribution for a set of targets. So for example, I want to be most accurate when predicting outcomes in a particular region, P star, X star, then we will just focus on design some experiments in order to improve the predicted distribution over that region. Okay? So now we have two different targets that we might be interested in. So for the problem setup and workflow, that's for Align, we are trying to jointly learn and amortize the inference model and also acquisition policy within just a single architecture. So how do we do that? We have a transformer and also have a policy head and inference head. So for the acquisition stage, given the history and also our target of the interest, the policy instantly proposes the next informative design X, and then we can do some experimentations to get corresponding Y. And then we can update history and feed into the Align again and get the next query. So we do it sequentially until we reach the budget or we have so we gathered enough of data. And once we have enough data, we can actually use the inference model to instantly estimate the target distributions. So it could be the posterior or posterior predictive, depends on our target specifier. Okay, so for the data structure, actually Align is quite similar to the transformer neural process or ACE that I mentioned before, except that we have a query set. So here the first thing is we have the context set, which consists of the history of the observations or experiment pairs. So it's X and the Y pairs. And then we have the query set, which contains the bunch of the candidate query point that we are trying to select the next design from this query set. So in this paper, we only care about we only takes this discrete setup, but it can be straightforwardly extended to continuous setup by building a continuous policy. So we don't need such a discrete set of the experiment designs. And then we have the target set, which contains the specific target specifier CASI. So, for example, for the parameter targets that I mentioned before, it's just the different indicators to indicate different theta. And also for the predicted targets, it's about the X star, a bunch of X star that we care. Then for the architecture side is very similar to it's a very standard transformer neural processes. It's just we have this query set, which also input into the embedding layers. So it's the same embedding layers, the X embeddings, and get corresponding embeddings. and then we can pass into the transformer layers and let the data to talk each other. And then we can output to the corresponding acquisition head. So acquisition head here select will assign some scores for each of design, and we just select the higher score from this acquisition head and choose as our next design. And for the inference head is quite similar to the ACE, so we're trying to predict the posterior or predict the posterior predictive or even the mixture of them. Okay. So for training this inference model, it's similar to ACE that we just train this Q5 by minimizing the negative log likelihood of the true target. So for parameter target, it's just that we estimate the marginal posteriors of each theta. And for the predicted target, it's just to maximize the log likelihood of the Y star given the X star and the DT. So it's very standard. And then about training the acquisition policy, so that's our last step. So we train actually using the reinforcement learning, so that's actually quite common in the previous, sometimes the BED literature. So, but the only thing is how do we choose our target objective? So it's about like, we want to choose the query that maximize the EIG or epic about target based on our different target specifier. It could be the parameter or the future predictions. But then how do we effectively estimate our objectives? So as like that's introduced before, that we could use some like lower bounds of the EIG or epic, like for example, the prior contrastive estimation or some other bounds to estimate. But the thing is here, we actually have a simpler method to estimate EIG and epic. So I will show you now. So recall that EIG actually equals to the entropy difference between the prior and the posterior, and then we can actually replace the one-step single EIG with the total EIG. So that's just the cumulative EIG over a whole trajectory because we are trying to build a non-myopic policy. So we just replace the PY given X, so that's about one design with a bunch of designs, so that's the whole data trajectories. And then we can also define the EIG over the parameters, part of the parameter space, so that's the theta S. And we just marginalize out those like nuisance parameters that we don't care about. So eventually, this is the SEIG defined over the theta S. And so we can see actually here we need to, in order to get SEIG, we have to rely on the true posterior distributions. But then like true posterior distribution, we couldn't have it. But how do you do that? So remember that we have the inference model. So we can just simply replace the true posterior with our inference model's posterior, estimated posterior. And then we can get, it's very easy to calculate the whole objective. Okay, and then for the epic, we could do the similar things that we just first have the original epic defined over one single design, and then we can replace it with the whole data distributions. And then we can have the true posterior predictive, but then we can just replace it with our estimated posterior predictive distributions provided by our inference model. So the insight is that we can actually use our learned inference model to guide the policy learning. So the idea is like the reward isn't some external score, for example, like a PCA bound, but we can just use the improvement in our own inference model's belief after seeing the new data from the query. So you can see it as like a self-guided or self-supervised reinforcement learning problem that our reward is directly calculated by the inference head. So each time, like before we collect some data, we can use the inference head to estimate the posterior or posterior predictive based on our targets, and then we can collect some data. And based on the newly collected data, we can ask the inference head to estimate posterior again, and we can use this posterior improvement to guide the training of the policy head. So that's the basic idea. And of course, our objective, the difference between the true EIG or epic between our objective is the expected KL divergence between the true posterior and our estimated posterior. So actually, it means like a more accurate Q5, the inference model, will result in a more effective training signal for the pi. So in practice, we have a warm-up stage that we first train over a lot, train the inference model only. And once the inference model's training signal is stable, then we can start to train the policy together. Okay. And the last thing that I want to mention is because we are trying to build a very flexible system, so to handle any target psi belongs to this psi space, we unify the acquisition objective, so we unify the parameter, target and also the prediction target. So the final objective for the acquisition policy is just taking the expectation over this peak size. So that's all of our like available target or interesting targets. So the idea is like for each round of the training, we just sample different targets psi from the peak size during the training. Okay, so now I will show you some interesting example that a line can do. The first one is about active learning for regression. So the idea is we try to efficiently learn unknown functions by sequentially choosing the most informative data points to query, so that we have some unknown points that are drawn from some unknown functions, and we are trying to predict those points and by actively collect some new points. Okay. So the classic choice of the surrogate model is the Gaussian process, but now we can replace it with the Alliance inference model. And of course, in order to like do the active learning, we also need to design different acquisition functions like uncertainty sampling or variance reduction or epic or bot. But now we can just replace it with Alliance acquisition policy. So everything can be done by Align. So here, and Align is trained entirely on a diverse set of the synthetic function that drawn from the Gaussian process priors. So here are some example functions that Align is trained on. So then the idea is we evaluate both on the in distribution settings. So that's a new function from the same prior that I just showed before, and also some out of training distributions. So we test on some classic benchmark functions that never seen during the training. So in order to test Align's generalization ability. So here I will show you an in distribution example. So here this one is just a randomly drawn GP prior functions, and there are some like black dots, which are our target points. And here, these blue lines and corresponding uncertainty estimation is provided by Align. So we can see how Align like query the data and also update its inference. So we can see actually after like 30 steps, Align can estimate the whole function quite well and provide a quite well calibrated uncertainty. And also, you can see this red line is the dotted this red dotted line is the Align's corresponding like target next to target. So, and we also test on another function that that's called gram C1D. So it's actually a slightly harder function because the length scale is quite small, and also the range of the function is quite small, and it's non-stationary. So we can also see like how Align performs on this function. So we can see also like after 30 steps, Align can estimate the whole function quite well. Okay. So we also did some like quantitative results compared with the standard GP-based methods. So equip GP with different acquisition functions, for example, like GP uncertainty sampling, GP epic, etc., and also the ACE. But ACE cannot actively query any data, so we have to equip ACE with different acquisition functions. So here we choose the ACE with the uncertainty sampling. So we compare with the we did some experiments on both synthetic functions drawn from the GP and also some different like benchmark functions, and Align outperformed other methods on like most of the benchmarks. And except for the active learning for regression, we can also test Align's unique ability to switch its goal at runtime, so without any retraining. So we can actually infer the underlying GP's hyperparameters, for example, like length scale or output scale. So the idea is we given a sub-function drawn from the GP, and we are trying to infer the GP's corresponding hyperparameters that can generate these functions. Okay, so here we test over on like 2D functions. So we have 2 length scale because that's 2D, and also output scale. And that's after the first round of the query. So that's the estimation provided by Align. That's the true, this red dotted line is the true values of the length scale and the scale. Okay. After 15 rounds, and that's after 30 rounds. So we can see after 30 rounds, Align can estimate the length scale and the scale quite well. And we also compare with the ACE, because ACE is another model that can infer this distribution without any retraining. We compare with ACE with different acquisition function, and we are much better than ACE in terms of the log probability. Okay. And then we also did some like standard Bayesian experiment design experiments. So that's a very standard experiment called location finding, that we are trying to find unknown locations of a hidden signal source by strategically choosing where to place the sensor to measure its strength. So here there's a blue blue star, which indicates the true location of the sound source. And that's the experiment design that's proposed by Align. And we can also estimate the posteriors about the true locations of the sound source, but that's previous untested BD method couldn't do. So we can see like how Align choose the next designs. So after like 6-7 steps, the Align can already estimate the true posteriors. There's no true posterior, but estimate the posteriors of the CTAS quite well. And we can also see all of the designs are concentrated around the true location of the sound source. Okay. And in the end of the experiments, I would like to share this psychometric experiment that I showed in the middle of the talk. So the task is we are trying to infer an observer's behavior parameters from their responses to varying stimuli. So we have like this kind of the psychometric function. It's controlled by 4 different parameters. And if we're trying to focus on the perceptual sensitivity, then we care about threshold and slope that I mentioned before. And if we care about another thing like response bias or attentional phenomena, then we care about guess rate and lapse rate. And we compare with 2 gold standard methods in this field. The first one is the Quest Plus. So it targets all parameters simultaneously. So that's not flexible. And another method is called psi marginal, which is a flexible method that can like focus on the parameter subset. But both of the methods are not untested. So when we care about threshold and the slope, we can see actually Align performs comparably to those gold standard method. And its Curie strategy concentrates stimuli near the threshold. So that's the Curie strategy, that's the number of steps, and that's the Curie's proposed by Align. Okay. And when the goal is to infer the guess rate and lapse rate, the Quest Plus actually performs suboptimally because it focuses on all of the parameters. And it couldn't concentrate on just the guess rate and lapse rate, which are harder to learn. But Align and psi marginal can actually just focus on the guess rate and lapse rate, so it achieves like very significantly better accuracy compared to the Quest Plus. And but now Align we can see select the easy stimuli at extreme values to best review the bias and lapses. So compared to this acquisition strategy, so we can see with the same model, but we can result in 2 different acquisition strategies. Okay, right. So today I introduced first the amortized conditioning engine and also the amortized active learning engine and inference engine. So that's only our first steps. So there are actually many exciting future directions. For example, the most important part is the scalability. So for now, ACE and Align can only like generalize well on like relatively low dimension tasks, but there are actually a lot of tasks which are existing in the high dimensional space. And also currently ACE and Align can only deal with like relatively small context points. So for example, like hundreds of points. But if we have like thousands of experiments or thousands of data points in order to query, then training such a model is very expensive because the quadratic complexity of the transformer. And so building like more powerful neural network is like another very exciting future direction. And also the dimensional agnostic architecture. So that's about like for different tasks, we might have like different input dimensions. And for each of the input dimensions, the previous method can only train separately, like train separate models for each of the tasks. So in order to amortize more things, how about we just build a dimensional agnostic architecture which can accept like different input dimensions. Okay, and the second part is about robustness. So this related to the model and primary specification that I didn't cover today. So that like Align or ACE is fully trained on the synthetic functions. So how do we decide what kind of synthetic function that we should generate is very important. So if the prior to generate this kind of the functions are misspecified to the real observed data, then Align and ACE cannot perform any can't have any good performance. So how to develop this kind of robust method is very important, and I think recently, Desi and other people have some recent work about robustness of the Bayesian experiment design. So, and the final thing is the expressiveness. So as I mentioned before, both ACE and Align can only estimate marginal posterior or marginal posterior predictive. So in order to estimate, to get the joint distribution, so correlation between the different parameters, then we can actually for example, using the autoregressive sampling. So we first, for example, we have 2 theta, we can first estimate the first theta, and we condition on first theta and estimate the next theta. Because with the ACE flexible architecture, we can do it very easily. But problems is AR sampling is very expensive. So if we have a very long sequence of the experiments or very high dimensional thetas, then each time we have to condition on the context set, and the context set has to do the self-attention, so it's really expensive to get joint distributions. So how do we develop a more quick and way to get joint distribution is also very interesting directions. Okay, so I think now the time is exactly 45 minutes. So in this talk, I first share Amortized condition engine, which can offer flexible and fast inference, and we are also the first one which can offer the prior amortizations. And also I introduced the Amortized active learning and inference engine, which is capable of doing both flexible and fast inference and data acquisition. So if you are interested in these two papers, you can just check them online. Okay, so I think that's all about my talk, and that's some reference. Okay, and thanks for listening. Any questions?
Really interesting. Please.
Thank you. So I will go a bit more in detail on the actual problems we have in physics on my talk on Thursday, but on slide 55.
Slide 55, yes.
I was wondering, so there you're solving the 55.
On 55, yes.
There you solve the problem of finding the posterior for given the for the 54 then. Given one value of theta. But for instance, in many physics experiments, what we are actually interested in is to find the placement, the posterior for the placement of the sensor, given that we can sample theta anywhere in that plane, so we can have theta anywhere. Does this method scale to that case?
Yes, so because we are meta-learning, so during the training stage, we are learning over a lot of different locations, so sampled.
So you sample theta over the
yes, theta everywhere. So in order to generalize over any location of the theta, so that's called meta-learning. So we can then in the tested stage, whenever the theta is located, then we can just perform the experiment design immediately.
Okay, and currently, to which dimensionality does it scale?
So for a line, currently actually it scales for example, for theta, we can scale up to 6 dimensions. But the thing is, training such a policy and both the inference method using the transformer is extremely expensive. So for this align model, standard align model, that's about parameter numbers about less than 1 million. And we have to train over on one H100 GPU for 3 days, the full 3 days. So it's actually quite expensive due to the this complexity of the transformer. But there are a lot of other works in the deep learning field that are trying to reduce this complexity. So yeah.
Please.
According to the EPIG, you consider the uncertainty of possible parameter, right?
No, we marginalize all the parameters. So we only care about future predictions. So we don't care about
So when you progress on the Gaussian process, you also only consider one set of hyperparameters?
Not one set of hyperparameters, but we draw from prior distributions of hyperparameters. For example, for length scale, we just randomly draw different length scales, and for each round, the length scale is different.
So, one at the back, Chris?
Yeah, thanks. That was really interesting. So you mentioned very early on that the uncertainty quantification is worse than the Gaussian process. Do you have any kind of theoretical guarantees about the uncertainty?
Yeah, actually, my current there's of course no any theoretical answer guarantee about using neural network, especially transformers. And I think there are a lot of people in that field are trying to get some theoretical things. But in here, we just the insight is that we should just continuously train the transformers. And our current observation is those bad the uncertainty estimation that provided by ACE, which is kind of crude. But we currently observe that if we continue training and we training for longer time, the transformer is super powerful, and eventually it will reach very similar uncertainty estimation with the GP. So that's quite amazing, I would say.
Michael? Hi. So thanks for the great talk. I have a question about the training of the parameters phi or the parameters of your model. So you said you use the predictive distributions also for the estimation of the expected information gain. So in a sense, you then have like two objectives. One is like the log likelihood that you can use to, or that you said you're using to learn the parameters phi. But then you also have expected information gain that depends on phi. So do you use both objectives for learning phi, or do you just keep the phi's fixed when you do the?
Actually, we do the joint chaining. So we first only chain the phi because the whole the experiment design part is relying on the phi. So we have to make sure the phi can provide a very reliable estimate. So we can see like once we have like a very stable chaining curve, so we can start to jointly refine the phi and also start to chain the policy. So
my question was not about the policy, but rather because the I goes depends on phi. So the gradient with respect to phi, does it only use the log likelihood, or does it also use the I?
The EIG.
The EIG.
Okay. Yeah. So actually, we don't actually propagate the gradient to the phi. So we just cut it and just use the EIG.
Second question was like you said like we could use it for Bayesian optimization.
Yeah.
When like also to propose what might be the optimal location. So P of X opt given the data. I think in a very early slide.
Yeah.
For that you need data exactly. So P of X opt given the n.
Yeah.
But you would need data on what are the optimal x's. For
that's one of the prerequisites for chaining such
so
things.
How do you get them?
So actually, we have some ways to generate the syntactic functions that we know exactly the optimal values of the functions. So, for example, we can put a quadratic bow or like a very large values to like synthetic function draw from GP, and we can ensure there's optimum values in that location. So that's the prerequisite. In order to train such a system, we have to know the true answers. During the Untitled.
So then in low dimensions, you may be able to sample a GP and do some grid search, or do you always use quadratics plus some other function?
I think in this paper we only use the GP priors, so we don't use any other functions drawn from some other.
So then to get the X opt to the GP priors, what do you do?
No, we couldn't get the X optimums with the GP priors, but we can actually assign, like we can manually design some X optimums and maybe drag the whole functions down, and we can get such functions.
Please.
So just following on the scalability, for acquisition of X, what was the dimensionality that you think it can scale up to for these GP priors kind of stuff?
So for this one, we test over like up to 7 dimensions, and it works. But it's also like it's quite hard to train, to be honest. So there are like currently there's also line for called like prior-fitted network, and that's just published on Nature, and they can actually afford like 500 features dimensions, and they essentially build a very like large inference models, and that parameter size is actually not very big. It's just 500, I think it's 5 millions of them. So compared to those large language models, it's quite tiny, but they can actually afford like 500 of the features dimensions. So it's extremely powerful, and we are also trying to like following their path to extend like the scalability of the A's or a line. And the current thing we found is like maybe this double layer search transformer, also related to dimensional agnostic architecture, is the key to scale up. So if we turn over like a different dimensions, then we might scale up to like a lot higher dimensions. So that's our current insight, but we haven't built such a model, and that's our future direction.
And just to follow up a little bit more, that in these GP priors, depending on the line scale, for example, of your earlier kernel, you can have much more complicated and wiggly functions that probably are much harder to
exactly.
right now.
Exactly.
So do you have an intuition how you could measure sort of this complexity of dimensionality versus also how those priors are wiggly and how to amortize this?
Yeah, that's a great question. So, like in practice, we just we sample from different kernels. We first sample the kernel types, and we sample the land scale. So we include the very small land scale and also large land scale. So we're trying to make this data set very diverse. But as you mentioned, like how to measure this complexity, we don't have like a metric for now. But I think it's very interesting because it relates to some real-world problems.
Yeah, because in your problems often you will have maybe quite broad, like some functions that.
Yeah, exactly. So actually in the paper we also show some case that when we fail. So if we training over a lot of complicated functions, but we suddenly input some very simple function, then it couldn't work. So it's all about a prior specification. We have to very carefully design a very powerful prior which can cover all of the function that we are trying to test on.
Please.
So one thing I didn't follow is about the prior, because you said that no matter what, you don't have to retrain the model. Can you elaborate on that?
Yes. So the idea is actually we again train over a lot of different priors. So for example, here you can see the first one is multimodal, and the second one is just a single Gaussian, and the third one is just the uniform distributions. So in the training stage, we just randomly draw a lot of priors and insert into the neural network, and trying to let the neural networks to learn the prior knowledge based on different shapes. And once it is trained over a lot of different priors, then we can amortize the prior, basically.
Okay, I get it.
You could look at, I don't know if you looked at doing Bayesian sensitivity analysis to the prior.
Yeah,
that'd be really
by
interesting.
Marvin and Steve Radev's work. Yeah, I think they also amortize the prior things. Yeah.
So if there's no more questions, let's thank Daolang again for a really interesting talk.